Okay, in this first lecture of this MOOC on I/O-efficient algorithms, we're going to introduce the abstract model that we're going to use in the rest of the course to analyze our algorithms. And then in the next lessons, well, we're going to see how to actually analyze algorithms in this model, and we're going to derive a lot of basic results in this area. But first, let's have a look at how a computer actually works. And what I'm going to tell you now is a very simplified view, but it suffices for our purposes, and it's sufficiently accurate, you could say, that it models at least a number of aspects that are very important when it comes to I/Os. Okay, so your computer, your laptop, well, it's going to have a main memory, but it's also going to have a hard disk. Okay, so what does a hard disk look like? Well, you see it in the picture. It's a little disk, and the data on this disk is stored in what are called tracks. So these are, well, concentric circles, you could say, on this disk, lots of them, and on these circles the data is stored. Right? And to read data, there's an arm with a head, and with this head you can read data when the head is positioned on top of the particular data element that you want to read. Okay? So what does it mean when you have to read some data item from the disk, or maybe write a data item to a particular position on the disk? What do you have to do? Well, first of all, you have to move the head, so it rotates until the head is on top of the track that contains the data element that you need. Okay? As you move this head, the disk is still spinning very quickly. Right? So when the head is finally above the right track, then you need to wait until the data item is actually right below the head. So that's the second thing you have to do. But first, moving the head is already going to take you around 10 milliseconds. Of course, that depends on the speed of your disk. Okay, so, and as I mentioned, after doing that, well, then you have to wait until the data item is below the head, and that waiting, well, you could be lucky and it's already quite close, or maybe you need almost a full rotation, but on average, let's say this is around a few milliseconds, let's say 3 milliseconds. Okay, once the data element is below the head, then you can read it. Okay, so what does it mean? The conclusion is that the total access time, as it's called, so the total time before you can start actually reading this particular element is, let's say, between 10 and 20 milliseconds. Okay, nowadays the computation time, or the clock time of modern processors is very high, this frequency. So it means that in the time that you need to access one item, you can actually do around 1 million CPU operations. Right? So if you had just had to add two numbers, let's say, that are already in the registers, then that's about 1 million times faster than just reading one particular item from your disk. Okay? And that shows that if you're not careful, that all these read and write operations are actually going to be the bottleneck of the runtime of your algorithm. But the way, what is nice is that once your head is in position, then reading other data elements that are stored next to the one that you were originally reading, that is going to be relatively fast, right? Because, well, you don't need to move the head anymore. The disk is already there, so if you now start sequentially reading, you just can read very quickly. So, roughly speaking, you could say, and again, of course, it depends on the characteristics of the disk, that the time it takes to position the head and wait until the track is at the right position, that time is about the same as from that point on reading the next 1,000 data items. Okay. Because of this, the way the operating system or the way your disk works is that actually, if you ask for a single item, you are not just getting that item, but you get a whole block of items, of data elements. Okay, so here you see, in the picture, you see this block. And so if you want to read a single element which is in this particular block, what you're going to get from the disk are all the items in this block. And the hope, you could say, of the operating system, of the whole system, is that, well, actually these other items will also be useful for you, for your computation, hopefully in the near future. So that when you need the next item from that block, you don't have to get it from disk anymore, but you already brought the whole block into your main memory. Okay, so that leads us to the abstract model that we're going to use to design and analyze our I/O efficient algorithms. We have an external memory, or a disk. So sometimes it will say external memory, or sometimes just disk. And we have an internal memory. Okay, and we have a CPU that can do the computations. And when we need to do a computation, the data needs to be in the internal memory. So if it's not yet in the internal memory, but on disk, on the external memory, we need to read it. And reading data is done in blocks. Okay, you don't get a single data element, you get a full block. So what are important parameters of the model? And these parameters we're also going to use in the analysis. Well, that's M, the size of the internal memory, and B, the size of one block. And as we will see, maybe now it's not completely clear, but it will become clear in the rest of this course, is that the number of IOs is going to depend not only on the algorithm and how much data you have, so the algorithm and N, but it's also going to depend on these parameters M and B. Okay, and what I said, B is the size of a block, and M is the size of the internal memory. And in this abstract model, we're not going to measure size in terms of megabytes or something like that, but in the number of objects that we can store, right? The number of numbers or pointers or something like that. So similarly to the input size N, we're not going to measure that in bits, but simply in the number of numbers, for instance, in the input if we want to sort. Also M and B are also measured in the number of elements. Sometimes we will use a technical assumption that says that, well, the internal memory size is relatively large compared to the block size. And in particular, sometimes we will need that this M is at least B squared. And in practice, this is not an issue. But sometimes in the computations, we will need this assumption. Okay, so the model I just gave is a pretty abstract model, and it's in some sense very far from reality, because you do not just have internal memory and a CPU, but actually between internal memory and CPU, you have lots of other levels of memory, as they're called. So you have a cache, you have an L3 cache, which is smaller than the internal memory. You have an L2 cache, which is a bit smaller than the L3 cache. You have L1 cache, and then you have registers. And finally, when data is in the registers, then the CPU can work on it. Okay, and actually the data transfer between these different levels, so for instance, if you want to move data from the internal memory to the L3 cache, again, this is not done by individual items, but this is done also using blocks. And the block size is going to be different between the different levels. So from external memory to internal memories, you have relatively big blocks. From internal memory to cache, you have to L3 cache, you have somewhat smaller blocks, and so on. Okay, so, and again, this is still not the whole picture, because nowadays you have maybe many cores on your chip and so on. But for us, the abstract model will be what we're going to use, and it's actually good enough in the sense that it highlights a lot of the important issues involved in algorithms that operate on data in the external memory. So what we're going to do in the next lesson is we're going to take this model and then we're going to show on a specific example how the analysis of the number of IOs of a particular algorithm works in this IO model.